weather is very humid, but such a series of praise make me sweat even more. So thanks a lot. I'm very happy to be in Brazil. I want to thank the CAPES, is that the name of the, for giving me this opportunity. And yeah, so I don't want to comment on my career, but you're right. The last part is the most important. I've been blessed with very many good students and postdocs, and most of the work I will be reporting is in fact related to their work. So, and in fact, there is one student of mine here, co-student. So I want to talk, so when Vladas proposed to come to Brazil, I said yes. And then the question was, what would I teach here? So I could choose on different things, random matrices or all sorts of questions on dynamics. And I chose to, initially I had even written a plan for a random matrix class, but finally I chose to speak on spin glasses. My contribution on spin glasses and my collaborators' contribution is mainly about dynamics. So that's what I want to go to. And that will be the second part of the class. But I chose to speak on spin glasses because the recent progress on statics, on equilibrium, is in my view spectacular. And I had, the domain had reached kind of some form of a plateau after the very important proof by Talagrand of what is called the Parisi formula. We'll get there. And for me, it was kind of stuck, the study of equilibrium. And in fact, recently, essentially by work of Panchenko, this thing is taking a really great shape. So I want to report on that, which at the same time a good occasion for me to learn this new progress, which I did. And so we'll start with statics, equilibrium question about spin glasses, and then we'll go to dynamics, and maybe in the end broaden what we've learned on dynamics to more, if we have time, more geometric problem like the trap models and all sorts of other disordered media questions. But so to start with the statics, so the spin glass problem is a question about statistical mechanics of disordered media. So when I prepared this, I realized that the literature I want to summarize for you is literally something like 4,000 or 5,000 pages long. I mean, it's incredible how hard people have worked on that. I mean, I'm talking about mathematicians, not, if you add the physicist literature, then you multiply by 10. So and it's still not over, even though there were recent very strong progress. So this is fascinating, and probably one has to explain why before doing anything about it. Spin glasses, it's not necessarily fascinating for its real-world physics application. If you count, I was told recently, and I'm not sure, I never checked that information, that the total amount of true spin glasses alloy on Earth is something like 5 grams, right? So we are not studying here a material that is prevalent, right? So I don't know if that's true, but in any case, the mass is very small. So there is this interest in understanding the origin of the question is about very strange magnetic properties of some alloys, and these are spin glasses. What is really remarkable for us are two things. First, the totally astonishing solution given to this problem in 1981 by Parisi, which is just a stroke of genius, and which we still do not understand. We can't even say what it did, right? Except if you accept using matrices with half a line and half a column, for instance, right? If you can manage this, then you can, but otherwise, it's really hard. So we still, there was this initial stroke of genius by Parisi, and then his school, who predicted essentially everything that has been proved up to now. And then, of course, the real interest for us mathematicians is that it is an incredible structure mathematically, which is far from exhausted, extremely rich, and there is a lot to be learned. And it's fun mathematics, even though it's hard. But so I do believe that the structure of this problem is by itself fundamental. what the history of this subject is the following. So before we go there, I was not sure of the audience before I came here. I asked Vladas, and I was not certain that everybody had, whether I should start with the basics of statistical mechanics. What is a Gibbs measure? What is a partition function, a free energy? And I don't know, but who has never heard these words here? Right, so I don't need to have an introduction. I wanted to make an introduction, a simple model like Curie-Weiss. So who, if you haven't, please raise your hand so that I can see you. 3, okay. All right, so I'll make a very short introduction for the 3 of you. And then maybe in a kind of private session, we could have some catch-up session with you. All right, but I don't want to bore the others too much with this. So here is the history of this, for those who don't know it. The model, so this is supposed to model strange magnetic alloys in which the couplings between 2 spins are not always positive. Right? They are positive or negative. So it's not ferromagnetic, and it's not anti-ferromagnetic. It's a mixture of both. Initially, here is I'll be very quick on that, but just so that you get the real model is extremely far from being even attacked by any means. The real model is the following. Imagine that you have spins which are distributed in space, in 3 space, and they are, say, distributed randomly, like a Poisson process. Right? Now imagine that the interaction between them is a function of their distance, and that this function of the distance has regions where it's positive and regions where it's negative, as is very natural with the usual potentials for electromagnetic interaction. Then, depending on the distance between 2 spins, you would have either a ferromagnetic, a positive interaction between them, or an anti-ferromagnetic, a negative interaction between them. So either they will want to be aligned or to be counter-aligned. So this is not really a random problem, except the randomness here comes from the modeling that we've made here, from the spatial positions of the atoms. But the interaction is not random. The interaction is simply a function of their distance, the distance being random now. So that's the real model. 3 space, a continuum model, and you take a reasonable potential, which has a region where it's negative. And so now the question is, what are the macroscopic properties of such an alloy? This question is not attacked, will not be attacked, I think, in the next, well, one should never say that, but it's very far from being doable. So at some point in the past, in fact in the 70s, people came up with the usual trick. That is, let's put this model, this randomness is very complex, let's put it on a grid, say on these 3, in 3D, on a cubic grid in 3D, and at each site of the grid you put a spin, plus or minus 1, or even more complicated spin, but let's just think of this. So you have 2 magnetic states, up or down. And now, in order to compensate from the fact that you have made the space much more regular than this Poisson process, you decide that the coupling between them, the interaction, is now random. Right? The interaction was random before as a function of the distance, which was random. Now you fix this on a grid, it's simpler, but you decide now that the interaction is random. That's the origin of the problem of random interactions. That's the real origin, the physics origin. Now it's a simpler problem geometrically, you are on a grid, but now you introduce randomness in the interaction. And an enormous simplification, because in the other model it's absolutely not true, of course, is that you assume that these interactions are IID, independent, same distribution. The identically distributed thing is not a crazy hypothesis, because if you have points in a Poisson cloud, this is reasonable. If the randomness came from the randomness of the distance, this is reasonable. but the independence is, of course, something different. But, okay, so IID. The important fact is to assume that these coupling, these interactions do not have a sign, right? So they should have a positive and a negative sign with positive probability. So that's the origin of the model, and this model now on the cube is called the Edwards-Anderson. So typically people would have chose initially, and that's the initial problem, to choose this interaction simply to be a plus or a minus with a certain probability. Very simple model. That's called the plus-minus-1 model. So that was done by Edwards and Anderson, and that's usually called the short-range spin-glass model. All right, they realized then that this deep simplification of the true model was in fact intractable. So this model, the Edwards-Anderson model, is still very, very open. The only physically there are lots of prediction. There are of course numerics about it, and there is a big fight that I'll come back to, a big scientific debate. This debate came since after this Edwards and Anderson paper. Then people thought, okay, we can't do it on a cubic grid, which would be like the Ising model in a simple situation. So let's do it on a complete graph. Let's do it in a midfield fashion. Forget the geometry, completely the geometry of the grid. Let's just do it in a mean field way. Oh, I will give meaning to that if you don't understand what I'm saying here, but I'm sure that many of you do. And that was the Sherrington-Kirkpatrick model, which came by I think in '75. The initial paper by Sherrington and Kirkpatrick was called a solvable model of a spin glass, right? So for them, it was the end of the story. It was a trivial exercise that was supposed to shed some light on the true problem, which was in fact itself a silly shadow of the real problem. But the solvable model of the spin glass, he was right. I mean, they were right. It is solvable because we are now solving it, but it took 35 years. The paper by the physicists, by Sherrington and Kirkpatrick, in fact, introduced the model, the spin glass, the mean field spin glass, which is the only thing we'll be studying here, and in fact gave a solution. And the solution was based on a very simple technique of physics, which is called the replica trick. And I'll come back to that. But they also noticed a problem that their solution at low temperature, in particular when you let temperature go to zero, was unphysical, but badly unphysical. The kind of unphysical that really physicists do not like. A negative entropy. That was really hard. So then they said something's wrong, but that's all. And this thing, was attacked by many physicists in this period until came this incredible paper by Parisi in '81, where Parisi introduced a solution to fix this problem at low temperature in the replica trick, and he introduced what is called the replica symmetry breaking trick, or the replica symmetry breaking scheme of Parisi. So he did it really as a stroke of genius. When you read the paper, it's incredible to even think of doing this. And what it means is not clear. And so when you talk to Giorgio Parisi and you ask him, how did you come to that? He said, I don't know. And he clearly doesn't know, but it clearly is fantastic. So if you want to be really inspired and awed, open this paper, or the book the classic book of '87 by Mézard, Parisi, and Virasoro, and you will see what real genius is, but how dark it is too, because you don't get anything out of it except the fact that now the knowledge a posteriori that he was essentially right. So that of course started a real business. I mean, in physics, then this method of the replica symmetry breaking method took off and covered an enormous amount of problems. And that's probably the reason why spin glasses became very important. In particular, in this book I just mentioned by Mézard, Parisi, and Virasoro, you see already a big section of the book is about applications to things which have nothing to do with physics. And this is a direction that this thing took off to, which is essentially combinatorics and combinatorial optimization, computer science type of problem, constraint optimizations, which are now, in fact, if you read the recent book by Meza and Montanari, that's what the direction of this is taken. And everything we're talking about here could go in that direction. There are many models of that flavor that have been treated by this non-rigorous replica symmetry breaking scheme, which we can expect to treat rigorously. So in this enormous class of problems, which contains the perceptron, the Hopfield model, and many others, the constraint satisfaction, KSAT, things of that nature. So you have an enormous range of models, which are very, finally, I would say that the real world importance of these things is more in this combinatorial optimization type of thing than purely in physics, but that have, that are there. And we will be treating only one model, the original model of spin glasses, and look at their statics and dynamics as much as we can. I will report an enormous number of works, so of course I will not be able to go in details for many of the proofs, but I will try to go in some detail of the proofs I do not know well, which is of course more fun for me. And not fair for you, but that's the deal. So now about what happened I start with this historical thing without writing for the moment any model or any kind, but I think it's really important to understand how things moved. So then we had some activities after this huge burst of activity in physics and the fine-tuning of this method of replica symmetry breaking to many other fields. So it's important to understand that what is done there is not the usual thing that mathematicians are nitpicking with physicists, saying we don't really understand the rigor of what you're doing, and so we come up with a proof. It's not that. It's not even things like supersymmetry. If you work a little bit, supersymmetry, the supersymmetric language of physics, is in fact a mathematical language. It's just the language of differential forms essentially, so we can make sense of it, even if it takes some pain translating. It's not the usual things where we mathematicians say, but this is not proved in physics. But we understand what we're talking about when we talk with physicists. Here, the real problem is we mathematicians make no sense of this replica symmetry breaking scheme, this replica method in general. And not only do we make no sense, but the physicists make no sense of it themselves. They know, they are shy about it. Inside of physics, I've been in many, as Vlad has said nicely, that has been a lot of my job to bring some problems from physics to math. And so to do that, you have to spend a lot of time with physicists. And some of my best friends are physicists, and I know them well. And in fact, they themselves, inside a theoretical physics group, they would make a difference between a proof using this scheme, this Parisi picture, and a proof not using it. And they would always mention with or without replica symmetry breaking scheme. They are utterly confident that this method works, but they understand that there is an epistemological problem. There is a question of what is this thing talking about, and that they don't know really. And as long as they don't know, then they are kind of shy about it. So there is a fundamental problem there which is still open. And to say the truth, what brought me to spin glasses initially, a long time ago now, is not at all the physics or the combinatorial optimization or this fantastic structure that we're uncovering now. It is something that is still completely open, which is to understand the original proof of Parisi as it is. Because my suspicion is that this has uncovered a fantastic structure, much deeper than any of the problems that are there, and that we still do not understand. For me, I'll be bold here, it's like when somebody discovered in Italy in the 16th century, or that there was a number whose square could be -1. Right? And then for a long, long time, this was a secret. You would use it or not use it, and then in order to understand that you were using something strange, you would call this number imaginary, because it doesn't exist. But still, it doesn't exist, but you can compute with it and find interesting things. We are in the same situation. We simply don't know the field of complex numbers. And there is something there that we still do not understand. So I believe that the subject is not over until we understand the original proof of Parisi. But this is a tall order. My suspicion is that after the recent results of Penchenko, maybe it's not such a tall order. Maybe there is something there that could open the door to the original thing that Parisi did. So my interest in that, and I will try to share that, is really intellectual. It's purely, what is this thing? How can a man come up with such an idea? And what is it? What is the real objects we're dealing with? Not how do we compute with them. So after this big, huge burst and enormous success in the physics world of the Parisi idea, after a while, of course, we had some interest from mathematicians. The early interest was, in fact, for problems that are looked at now as totally trivial, which were, but at the time, of course, I can tell you they were not. It was about the trivial behavior of spin glasses, that is the high temperature regime. Deep inside the high temperature regime. So you had initial work by Fröhlich and Bouvier, you had initial work by Zegarlinsky, by Eisenman, Leibowitz and Ruel, and then by Comets and Neveu in France. All that are now essentially tiny results compared to what we understand. But they were the first steps, and that brought the subject in math. At the same time, realizing that the study of statics, equilibrium, was essentially impossible, I thought that we could start directly with because if you look directly with dynamics, it looks like a strange idea. In statistical physics, you better understand equilibrium before you understand the dynamics to equilibrium. But you will see why this is not a ridiculous idea. Because here, the dynamics are the convergence to equilibrium at low temperature is so slow that in fact, what you sample of the Gibbs of the space by dynamics is very different from the Gibbs measure. And this very slow convergence to equilibrium, this strange dynamical behavior is what really interested me. So it's a different problem that we also started in the 90s, essentially initially with Alice Guillonnet and then with many other collaborators. The real breakthrough, so in dynamics we moved on this type of things, essentially with Anton Bouvier, Véronique Gérard, and then many of my younger collaborators, Jiří Černý, Honor Gun, and many others. But the real progress on the equilibrium problem came when Michel Talagrand got involved. And that is in the 90s. Initially, what he did was essentially apply some of his concentration inequalities to attack the problem. Very quickly, he realized, so my take on this was, if you open the Mézard-Parisi-Virasoro book, which was the Bible on that at this point, you had a few different chapters, and there was a chapter 5 on dynamics, which is where I started, and there was chapter 4 on what is called the cavity method. So the cavity method was a method to prove the equilibrium results, which was an alternative to the crazy Parisi scheme. And this alternative seemed like you could make sense of it. Right? So what is the cavity method in a nutshell? It's you have a system with n spins. Now you just do induction on the number of spin. You add one more spin, and you look at it as you look at the magnetic field that the n spin produce on this one, and you try to average this magnetic field in some sense. And so by this, doing a recursion, obtaining a recursive equation on the size. Very broadly said. So Talagrand took this as a method maybe to get into the problem, and he did some serious progress on the high temperature regime using this. But realized very quickly that this was stuck. That is, at some point, this could not get even to the phase transition, and even less to the interesting low temperature regime, which is, as always in a hard model, what you want to understand. The breakthrough then came through work by Guerra. So Guerra had worked on this for a very long time and came up in 2002 or 3 with a great idea. And an idea, in fact, Guerra and then Guerra and his student at this point, Toninelli, came up with an interpolation scheme that was brilliant and that gave them one bound, which was fundamental, and also a deep understanding of what was happening. As soon as this thing happened, Talleyrand jumped in because he was ready. He had realized that the cavity method could not really work. And this new tool, I mean, he jumped in, and in a few months, essentially, he proved the Parisi formula. So he proved that in some sense, at least for part of the picture, Parisi was right. And so that was in 2003, 4, 5, or something of that nature. And then the story since then has been that we had the Parisi formula. Again, if you be patient, because all that will be explained at length, which gives the behavior of the partition function of the model, the free energy. But the real problem was then to understand the behavior of the Gibbs measure, right, itself. And there was a big conjecture, which is called the ultrametric conjecture of Parisi, and ultrametricity conjecture, which in some sense simply in a language that we can understand give credence to the original prediction of Parisi. This was very open, and the last 7 years or something, or I don't know, 8, have seen a considerable progress in that direction, and in particular recently we have settled with, at least in the class of model I will explain, with a full proof of ultrametricity, which really confirms what Parisi had predicted on the structure of the equilibrium at low temperature. This doesn't mean that the problem, even without my high goal, which is to understand the original, so first it doesn't explain really the original proof of Parisi at all. It just confirms it by a way that we can understand, and the structure of the solution, as I said, is mathematically extremely interesting. But then there is, still there are many, many open questions and that are left all over. It's a type of model where, for instance, the high temperature region is not at all trivial. There are many, many questions left, even in the high temperature, let's say above the AT line or on the right of the AT line. The AT line is being the line that separates the two regions. There are a million questions, of course, for the spin glass, for the interesting region itself. And then once this is understood for the class of model I'll be talking about, there are an even larger number of classes of model where we don't know much. All right. I didn't mention one thing, which is this recent progress has been done. So after Guerra and Talleyrand main contribution. So first, of course, there's this great book by Talleyrand on spin glasses that came just after his proof of or in fact, right before his proof of the Parisi formula. And recently, or last year or year and a half ago, he published 2 more volumes in Springer, Gudleon, on spin glasses, which are extraordinary. I mean, fantastic. You can spend easily a year reading them, and you will not waste your year. So that's the Talleyrand track. But then, of course, Panchenko, who initially worked with Talleyrand, has recently solved some of these questions, and I think will solve many more if the proof hold up. But in the meantime, there were many, many others who worked on that. So maybe the important contribution should be mentioned of Eisenman all along this thing. I mentioned that he started very early on. Then there was his work with many people, in particular what is now called the ASS scheme, the Eisenman Sim-star scheme, which will play a big role in the proof of one of the bounds of the Parisi formula. And maybe more importantly than that even, there is another thing, which is the Eisenman-Contucci stability property, which I think is has played a crucial role in the development of that. And maybe even more importantly, this initiation in a paper of Eisenman and Arguin some time ago now of what is realizing the role of what is called the of exchangeability. Let me put it that way. So that's a long line of results, and then there is another line of results which has proved to be very important, and we will survey all that, which is the of course in the line of results of Guerra you had what is called this very important work of Ghirlanda and Guerra, who introduced what is called the Ghirlanda-Guerra identities, which we'll see are the center of this whole thing. And another completely different thing, I should mention the following. In 82, after this 81 paper by Parisi, you had Bernard Derrida in Paris, who decided that he wanted to understand, so at this point Bernard was probably very young, 30 years ago, yeah. So. And he decided that he wanted to understand this model in a simpler setting. Bernard Derrida is extraordinarily gifted to find the right models. And he introduced a completely trivial model, which is called the random energy model, which I will call the REM, R-E-M, random energy model, on which, of course, you can compute everything you want, but you know, it's not clear that it should have any relevance to the hard models that we're talking about. But it does. In fact, Bernard introduced the REM, and very soon thereafter, what is called the GREM. The GREM is the generalized random energy model. And this model, the GREM, is supposed to have in it, from the start, this ultrametric structure. You still don't know what that is, but that's the grail, that's the holy grail, that's what we want to get from the true models, in the model itself. So Bernard started from the idea, if we have to have in the end some kind of ultrametricity coming from a model which is not initially ultrametric, let's first study the ultrametric models by themselves. And that's what he did. And from this, then things evolved in the direction of understanding, say, the limits of these models, the GREM. And the limits of that are called, can be called many things, but they are now called the Ruel cascades, because Ruel introduced those cascades as limiting objects in the 80s. And for Ruel, it was clear that this was a limit of the GREM. In fact, it's not that easy to prove. It took quite a bit of work done by Anton Bovier and Irina Kurkova in the 2005 or something like that, to prove that. So you had this structure which was a priori completely separated from the true models. They were supposed to be the simple models, the models that are a priori ultrametric that you can study, and there are limits, which are those real cascades. Those real cascades have been also studied independently, I mean, more in depth by Bolthausen and Snitman, and they're also sometimes called, the limiting objects are called the Bolthausen-Snitman coalescence. And these objects, as we will see, proving that these objects are also, the limiting objects are also related to the limiting behavior of the hard model, is really what the Parisi conjecture is about. And so it was very instrumental to have understood these things in order to understand how they could play a role in the solution of the hard models. So now we know that they do play a role, and the way this is brought about is in fact still very ad hoc. So in some sense here, in this way these two things get together, there is something of this understanding that really deeply, I think, is probably equivalent to understanding the initial proof of Parisi. So this is the very roughly, and I'm forgetting a million important contributions here, that what the story is and what the kind of papers I will try to summarize. So what are the models that we'll be talking about? I will talk about three classes of models, in fact. the class of model that include the Sherrington-Kirkpatrick model, this initial model I talked about, which is called the mixed spins, the general model of spin glasses, on the cube, right? Which means with hard spins. Then we'll look at a different version of this model, which is called the spherical models, where the spins are soft, are in a sphere. So the traditional view is that the spherical trick, that is changing the model from hard spin to spherical spins, this goes back to Katz, to Mark Katz, is supposed to be a simple simplification. In this case, if you read the paper by Talagon on that, it's certainly not a simplification. It's pretty hard, but we'll see some recent progress on these models that Tuca and I and Jiří Černý have made, and that you heard here in Brazil if you were around something like 2 years ago. And I will talk also about this ultrametric model, the REM and GREM, which are supposed to be the ideal word, the simple word. Right? So we have 3 classes of model, but the really important ones that the whole focus was initially on are the class of spin glasses on SK. All right, so with that, let me introduce those models. Are there any questions on this history? I mean, of course, it's hard to question the history, but maybe you can challenge my historical views if you have. All right, so since nobody challenged it, now let me get into controversial territory. Everything I said up to now, I think, is reasonable. It might not be fair just because I forget some people, and I don't want to forget anybody here. But what I'm going to say now is more interesting in the sense of it's a hot debate. If you go back in history, now let's assume that we have understood everything about the Sherrington-Kirkpatrick model and this class of model, which is not the case, but at least we are on a good path now, a good track. So you have this whole philosophy of mean field spin glasses that was given by Parisi, and that is now kind of vindicated. It's true for mean field models. Okay, so let's go one step back in history. Before this Sherrington-Kirkpatrick, we had the Edwards and Anderson model, which I mentioned to you, which was on the lattice. So what kind of information can you get from the mean field model to the cubic model, right? The short range model? Typically, in any model of statistical mechanics, when you understand things on the mean field case, the mean field case is supposed to be the limit in large dimensions of the finite dimensional models. But this is really the debate. So is there a dimension above which the lessons you learn from mean field cases, from Parisi, are giving you any kind of information on what's happening on a geometric model, or not? So the critical dimension, the dimension above which the Parisi picture could be valuable, if you ask a physicist, he will tell you 8. Sometimes 6, depending on what kind of problem you ask. But there is a whole school, also of physicists, and now very well illustrated in my own department by Chuck Newman, my colleague, and Dan Stein, that think that, in fact, the critical dimension is infinite, which means that the Parisi picture is never valid for short-range models, right? So this mean field thing is beautiful and structurally fantastic, but doesn't bring any information for the model in finite dimensions. And so there has been this long debate. Of course, in the physics world, it's hard to settle. I've sat in many talks where you had a young physicist showing numerical experiments trying to prove that Parisi was right or that Parisi was wrong. And when you try to simulate a spin glass in 3D, it's extremely hard. So what they could simulate are tiny pieces of spin glasses, and the results are always difficult to interpret. They claim, of course, they do claim that they are not hard to interpret, but then there is this view so that's called the droplet picture. I won't go there, of Fisher and Hughes, that say that this droplet picture completely excludes the idea that Parisi would be right in finite dimension. And this droplet picture has been taken up by Chuck and Dan, Chuck Newman and Dan Stein. And for a long time, what they've done since the 90s was to list all sorts of crazy things that would be true if the Parisi picture were true. Things that were so crazy that they would convince you immediately that it cannot happen. But they would convince you because, of course, nature has to be reasonable. But there was no mathematical contradiction, except it looked really completely bizarre. But recently, there's a major contribution by Arguin again. I'm trying to give them in the order of alphabetical order. Damron, Neumann, and Stein, which shows that this Neumann-Stein picture is at least in 2D on a half space valid. So they kind of contradict the picture by Parisi, at least in 2D on a half space. So that's an important thing to understand, an important caveat. It's not at all clear that the Parisi picture and this Fisher-Hughes picture type of things coexist in finite dimension, in the sense that there is a finite dimension below which you have one and above which you have the other. We still don't know. So it might be that this whole Parisi thing brings no information on the finite connectivity problem, on finite dimensions. Except, of course, this would be immediately challenged by Parisi and his school, or I don't know, Andrea Montanari, if he were around, because what they've been doing in the last, 10 years, is to study the same kind of model on finite connectivity graphs, right? Not the complete graph where the degrees is diverging, but on finite connectivity graphs, say where each vertex has 4 neighbors, like in Z2, but which are chosen randomly. Take a graph of size n, degree regular, random, and then put a spin glass on it. And on these models, of course, then you see that the Parisi picture is in fact correct. So it's not the finite connectivity that is important. That is important because in this model, the main thrust of the proofs is that on those models I just mentioned, and I don't think I will have time to go there, but if I have, it would be fun. The important part is that those graphs, a random regular graph on n vertices, is locally a tree. Right? So because it's locally a tree, it's natural that it behaves like a mean field model. By that I mean if you take a point at random in a random regular graph, you, at a distance constant times log n, you see essentially only a tree, no loops. But remember, log n is huge, because in fact the diameter of the graph is itself another constant time log n. So essentially in the big chunk of the graph you see only a tree. Right? Whereas of course if you take another regular graph, not random, Z2, then you don't have to go far to find a loop. Right? The loops are just all over. So that's a real difference. All right, so the debate is not over. It's fun, and there's beautiful mathematics being done on both sides. And, but I won't go there. And then, of course, now I unwrap my whole lecture here. Once we have understood the Parisi picture, maybe its relevance in finite dimension or its non-relevance in finite dimension, once we understand the finite dimensional problems of Edwards and Anderson better than I think the only mathematical result, serious mathematical result we have is this recent paper I mentioned by Arguin, Damron, Neumann, and Stein. Once this is done, maybe 20 years from now, we still have to go back to the initial problem where the randomness was spatial. But that, as I said, there's nothing even begun in this area. So I think maybe I should have a little break right now, 5 minutes, and then I start with the no more blah blah and just the models and all that. All right? Statistical mechanics. Let me have here maybe 2 boards to explain what the story is about. Okay? And this will be too short for you, but then we'll spend the rest of the time on this. And I'm sure you can have some help from some others here to catch up. So the idea is the following. You have, so what is a statistical mechanics model? Is you have a space, let's say sigma. This is the configuration space. So that's an element, sigma in sigma is a configuration. So sigma is the space, the set of all possible configurations of your system. And then on it, you have, so that's the first thing. Of course, I'm light here on technicalities. You want this configuration space to be reasonable, but let's not go there for the moment. Second element after that, you need a function. On sigma, which is called the Hamiltonian, but mathematically it's just a function, or sometimes called the energy. So it's a function simply that goes from sigma to the real numbers, and which to each sigma defines an h of sigma, which will be called the Hamilton. H is for Hamiltonian, and defines the energy of the configuration sigma. Right? Simple. Third structure. So what do you want to do with that, by the way? So typically, if you're not a statistical physicist or mathematician doing that, but more, for instance, a computer scientist, typically, this would be the state of a system, a configuration. This would be something you typically try to maximize, you optimize. Let's imagine we're doing optimization. So let's imagine that what you're really interested in is finding the minimum of this function. And this space is complicated and it's hard to find the minimum. So one question is that we will call, of course, in terms of physics language, is find the minimum of h of sigma for sigma in h. That's called, this is the minimal energy, and the place where this minimum is achieved, if it is achieved, are called the ground states. For obvious reasons. That's a state, ground, because it means where the energy is minimal. So that's a hard question, which has nothing to do with probability, right? You have an h, a function you want to minimize. Of course, it's a huge domain of mathematics and computer science to know how to find these things. Then the statistical mechanics method is to introduce different, what physicists call ensembles. So if you're not a physicist, remember one thing. Ensemble means probability distribution and not set, right? So there are different ensembles. Here in this context, you could introduce typically two. So the canonical ensemble, or the Gibbs measure, is to do the following. Is to look at this measure. Maybe you could have an a priori measure, say, let me call it alpha. Alpha is a probability measure on sigma. And you would define this measure, dg of sigma, g like Gibbs. Let me take this coherent notation. And of course, this might not be the probability measure, so you have to normalize. And z is simply the integral of this. And this is called, so z is called the partition function. And this is called the canonical ensemble, or the Gibbs measure. All right? So obviously, at least it looks like, if this measure is not too crazy, that when you let this beta go to infinity, right, the main contribution to this measure will be the places where h is minimal. Right? If beta is very large, only the places where h is small should play a role. So beta very large should allow you to recover this, maybe. Here, beta is usually also denoted as 1. It's so one thing that we mathematicians keep forgetting are absolute constant. The physicist would be appalled at this. T here is what is, so 1 over beta is called the temperature. But in fact, the physicist would put a Boltzmann constant here, a K, but we don't care about the constant. Right? So getting beta to be very large means getting temperature to be 0. to go to 0. So at very low temperature, such a model should give you a grasp of the structure of the minima of this function. At temperature, when beta is 0, which means infinite temperature, then of course this whole term disappears, the influence of H completely disappears, and what you study is simply the probability measure A, which is, think of it like a uniform measure on sigma. All right, so that's the canonical ensemble. There would be another one that we will study maybe a little bit, would be to do the following. I won't write it. It's called the microcanonical ensemble. It would consist in doing the following. You just restrict, or maybe I could write it here. Let's say you restrict yourself to the case, so you just look at the set of, let me give it a B like band, where the set of sigmas such that the energy is equal to a constant, or at least is in a little band, say A plus epsilon. Right? And now you look at, so this is, now instead of looking at the energy, the whole space, and then weight the mass of a point by essentially exponential of negative energy, what you do here, you restrict the energy to a given value or a given band, and you take the uniform measure, say you take the alpha measure, restricted to B essentially. Right? So you have alpha, something like the uniform measure, and you just look at the distribution of on the space of states whose energy is fixed. Right? That's called a microcanonical ensemble. And in fact, these two different, so this is of course parameterized by A and maybe epsilon here. So this of course will depend on, there's a vague general principle in physics that says that those two ensembles will give you similar results. Okay, that's called the equivalence of ensembles. Of course, here you have one parameter, which is beta, temperature. Here you have another parameter, which is the energy level, say A. And the idea is that when you have lower temperature, very low temperature, it should concentrate on space, on values of, on configurations whose energy is in the typical value A. So there should be a correspondence between A and beta, right, for this equivalence of ensembles to be the same. But we won't go there for the moment. So not too much. So the idea is, let's go back to this. So this is just an excursion into the microcanonical ensemble. Now the question is, what do we do with this Gibbs measure? So there are essentially two questions. Question one, and of course you have to trust the experience of, so this is still for the three who've never seen that, a long standing experience, that understanding Z is the first step. And once you understand Z, you can derive a very large number of interesting quantities out of that. So understanding Z, that's the question one. Understanding the partition function. So, and more precisely understanding log Z. And so of course here, we have put no parameter. So if you have a fixed space, a fixed H, a fixed beta, hard to do anything. So typically what we have is that this configuration space, and now I would introduce an N, we have a sequence of configuration spaces. And then we have a sequence of energies and of Gibbs measures. And this N here, this parameter N is of course typically the size, the volume of the system, the size of the system, the number of particles. And we will want to understand that, of course, that's statistical mechanics, of course, is to understand it when we have a large population. When N is large, we have a big population, a large number of particles. Otherwise, of course, there is no asymptotic regime. So the typical behavior, what we want to understand typically is this. And we are happy when this limit exists. It's not always clear that it does, but we're happy then when it does. And so this limit will be called the free energy. will, of course, depend typically on beta, and then many other parameters if you have them. And we want to understand this. This Zn, of course, depends on beta and on the size of the system. So the first question is to understand the partition function, or at least this limit, to understand this object here. Typically, this f is given by a variational principle. And f can be studied, and what you see is that the behavior of this function here typically depends, an interesting model depends very much on beta. And there are different regions of beta, beta large and beta small, so low temperature and high temperature, where the behavior of this f is different. And that's usually called the phase transition, when this transition is sharp. The next question, so that's question one. The next question is, of course, understanding the behavior, the asymptotic behavior of the Gibbs measure. Asymptotic meaning when n goes to infinity. Right? So that's the two important questions. So typically the Gibbs measure will behave. So let's look at it. Here, let's imagine this is a uniform measure. When beta is 0, the Gibbs measure is like the uniform measure. When beta is very large, you might expect that the Gibbs measure is very concentrated on the minima of h. So it's very different from a uniform measure. And so in between, there is a transition. And that's the phase transition. So you want to understand where the transition happens, which you can usually detect here. And then the behavior of the Gibbs measure in the two different domains of parameters for beta. So this is a vague question. There is something deep behind the way this question should be formulated. What does it mean, understanding the behavior of a Gibbs measure? Typically, you have a sequence of of probability measures on the spaces sigma n. How do you understand the limiting behavior of a sequence of probability measures on different spaces? Right? So there are some situations where it is clear that, in fact, there is a limiting space. Right? Imagine that those models, those configurations are, for instance, spin configuration on a box of Z2. And n is the size of the box. When you let the box grow, you may naturally imagine that the Gibbs measure should define something, a probability measure, on the whole of Z2. Right? So then there is some limiting object which is natural. But otherwise, it's not clear it's not always clear that there is such a thing. And so how do you understand the limiting behavior? What has emerged in all models of statistical physics is that there is usually what is called an order parameter, which means, in fact, essentially one observable, one function of the random system which controls the whole thing. And depending on its behavior, the Gibbs measure will be doing this or doing that. So you want to understand one order parameter. It's not always clear what this order parameter is. So in simple models of magnetism, like Curie-Weiss or Ising, the order parameter, and I might say a word about that for you three, but the order parameter we all know is magnetization. It's one number, one random number. It's dimension 1. The beautiful thing, and the reason the mathematical structure of spin glasses is interesting, is that the order parameter is infinite dimensional. The order parameter will be, as we will see, a probability measure on the interval 0, 1. So instead of being one number, it's an infinite dimensional object, which of course makes the whole thing much deeper and harder to manipulate. The fact that this order parameter was the right order parameter was in fact understood from the beginning by Parisi. Okay, so it's not a discovery of mathematicians after Parisi. It was right there in the initial paper. Okay, so the important notion here is the order parameter. understanding this, I think it's a very well posed mathematical question. This question is not very well posed. How do you understand the behavior of a sequence of probability measures and a sequence of spaces? It's not clear. And we will see here that it took 30 years to really understand what this means in the context of spin glasses. All right, so this is my 10 minutes introduction to statistical mechanics. For the 3 that didn't know that, questions on this? Okay, so let me give you first the natural examples. So examples of first on the space sigma n. So typically it could be, so let's imagine that your configuration now can be simply this. So this means that a configuration sigma is simply a collection of plus and minus 1. Say. That's a configuration. And that's a length n thing. So it's a collection of n spins, right, which are either plus or minus 1. That's one configuration. And then you have to define an energy for that. But before going there, so that's one model. So geometrically, what is this? These are the vertices of a hypercube. This is, you look at the cube, right, of size in dimension n. N is the number of particles, here the number of spins. And you just look at the vertices of the cube, right? So geometrically, this is the hypercube. Right? We say hyper simply because we're in dimension more than 3. Now, it's clear that this minus 1, 1 to the n, we could now take something else, which is, here's another type of model that we could look at. It will be the sphere of radius square root of n. So that's the set of sigmas, which are vectors in Rn, whose norm is square root of n, Euclidean norm. So Euclidean norm is square root of n, means simply the sum of sigma I square is n. Right? So this is the sphere centered at 0 of radius square root of n. Okay? Obviously, and it's important to notice it right now, this guy is included in that guy. Right? If you take such a configuration, take the sum of squares, it's always n. The square of each of these guys is 1, and you add n of them. Right? So the vertices of the hyper in dimension 2, it's of course simply this picture. You have this radius is square root of 2, if this, and then you. So one space is the sphere, the other are just these 4 points. Okay? So in this configuration, sigma is a vector, it's a continuous vector. This here it's a discrete object. Right? This is a manifold, this is just a discrete object. And so what is the advantage of this one over that one a priori? Or the other way around. What is the advantage of that one over that one? This one is nice because it's discrete. So all sorts of questions about integrals, measurability, everything like that is trivial. This one is nice because it's continuous, but more importantly because of one thing. This configuration here, space, has the symmetry of the sphere. It has, by definition, the orthogonal group. You can act on this by any orthogonal transformation of Rn, and this stays the same, right? Whereas this is not like that. If I take a rotation here, which is, say, of 45 degrees, or I don't know, 10 degrees, I don't stay fixed on this, right? But I stay on the sphere, right? So there is more, here the group of invariants of this space is large, as the orthogonal group, whereas here it's discrete, it's small. There's many more symmetries here than there. Right? So that a priori makes this model supposed to be simpler. But okay, I didn't say what the measure alpha was. So alpha here would simply be the uniform measure. Right? So what is the measure, the base measure I called alpha over there would simply be here the uniform measure on this, which is alpha of sigma for any sigma would be 1 over 2 to the n. Since you have 2 to the n possible points, configurations here, the uniform measure is just this. All right? And here the measure alpha would just be the surface measure, the uniform measure 2 if you want. Which now is the Lebesgue measure on the sphere, or the Riemann measure, I don't know how you call it. Okay, the uniform measure on the sphere. So here you would have the uniform measure, each of these things would have a mass 1/4, and now when you take any point on the circle, it would just have the uniform measure on the circle, right? Now, these are about the spaces. Now, what about the energies? So, because this is the background, now I need to give the energy. So now let me introduce some examples of energies of Hamiltonians. So of course the simplest model is the Curie-Weiss model. So this model was introduced, as you know, in the beginning of the 20th century, first by Curie, and then Weiss worked on it, to try to get the fundamental phase transition in magnetism between ferromagnetic and paramagnetic behavior in a very simplified model. Right? So what was that? The energy here would simply be, so here sigma n is minus 1 to the n. So what Curie said was, so he was thinking about a piece of iron, and he said, all right, there are some magnetic blocks in there. Each magnetic block I will give simply one number, which is it's either magnetized in one direction or the other, plus or minus. And then I have this collection of n magnetic blocks, n being large, because my piece of metal is macroscopic and these blocks are microscopic. And there are all sorts of possible interaction between them. And the geometry of this is complicated, so I don't know how to do that. So I will just ignore the geometry and say that every block interacts with every other block in a very simple way. And the simple way would be to say that they tend to want to be in the same direction, right? So the energy that he chose, the Curie-Weiss energy, in this case is simply minus J, some constant, over n, sum of sigma I, sigma j, over all possible ij, and maybe plus H sum of sigma I. So the important thing here is that J is a strictly positive number. This is crucial. It's a ferromagnetic system. All right, so that's a very simple model to study. I won't do. I would be ashamed to do that in front of some of my colleagues here, but if you want, we could have a private session for that. So look at what this means, right? For those who've never seen it, forget this thing. So this H is called the external magnetic field. J is called the coupling constant, and it's positive, which in this case is called, the model is called ferromagnetic. Let's for a moment take H equals 0 and just understand what this does. Right? Each of these terms here, let's look first at the problem of finding the ground state. What is the minimum of this function? Forget H. Each of these terms here is either plus or minus 1. Right? If they have the same sign, if they are both pointing in the same direction, then this is plus. If they are both pointing in different directions, then this is minus. If you want to make this minimal, because of this negative sign and the fact that J is positive, you want to make this maximal. To make this maximal, you want to align all the spins. Right? So it's clear that if you take all the sigmas to be plus 1, you will have the maximal value. And if you take all the sigmas to be minus 1, you will have the same value, in fact, in this case, when this term is not here. Right? So you have an absolute maximum and absolute minimum that you know. It's not hard. In this case, finding the ground state is trivial. Right? So now, when you look at the Gibbs measure at positive temperature, First, when the temperature is very small again, so here what is measure, let me remind you, it's just this. Okay, so it's clear that for small beta, and this is what you find here, this should be like the uniform measure. And at large beta, you should feel the influence of the spin that want to be aligned, because the minimum, that's where the minimum are. Right? So you should see, so when you have a uniform measure, the spins do not want to be aligned. They are all in random order. Right? And when they want to be aligned, you can feel it. So how do you feel the difference between spins that are aligned and not aligned? In fact, one way to look at it is, and that's the right way, is to look at the proportion of spins that are pointing in the same direction. And for that, one way is to look at the magnetization. Magnetization, mean magnetization per site. So you just look at this. You just do the sum of these guys, which are plus or minus 1. Right? And by a very simple algebraic thing, it's just equivalent to looking at the proportion of sites that are plus 1, say. Normalize. So this is the total magnetization, and this is the mean magnetization. Right? And the question is whether, so if you have a uniform measure, if beta is 0, if these guys are distributed as being plus or minus 1 with equal probability, it's clear by the law of large number that this goes to 0. Right? So the mean magnetization should be 0. Again, here h equals 0. When they tend to be all aligned in one direction, then the mean magnetization could be either plus 1, if they're all 1, or negative 1. Right? Okay, so then you should see, and in this context, on the contrary, this mean magnetization should be concentrated on two completely different values. Right? With different probabilities. So that's the phase transition. And this phenomenon just, what I'm saying here happens really. So if, I don't want to, I'm sure that many of you have taught that, so I don't want to do that here, but if there is need for saying more on this trivial model, just ask me. I don't know, is there a need now? Should I? Alex, what do you think? Good if I don't do it. All right. Of course, I didn't discuss the role of this guy. Right. So now let's add this in. When you have this h here, it means that, you can see that, let's say h is positive. Then you want, if you want this to be minimal, remember there is a negative sign in front of it. So you want this, to be minimal. So I should have put okay, it's just a matter of parameterizing in the right way. So if I want this to be minimal now, I'd better have this guy and this guy to be the same sign. And this, remember, is simply the magnetization, apart from a factor n. So it's clear that if I put a positive guy here, I will tend to obtain a positive magnetization. This thing pushes in one direction, so it breaks the symmetry. So here, remember, at low temperature, you either had everybody plus or everybody minus, but when you add this term here, then you choose one of them, right? Either all plus or all minus, depending on the sign of this guy. So when you put the lesson here that when you put a magnetic field, then you have only one minimum. When you put no magnetic field, you may have this coexistence of two different behavior, which is called a phase transition. Right? So here's the lesson that you get from this. You have what is called a phase diagram, which is here you put the temperature, which remember is 1 over beta, and here you put the external magnetic field. And the behavior is like this. There's a critical value of the temperature, or beta. Then there is this region here, which is special. And everything else here, so this whole region is what we could call the high temperature region, even though here you are at low temperature, as long as you have a positive magnetic field. So this whole thing is the paramagnetic phase, which in some sense, which is not completely true, in some sense behaves as if you had a uniform measure. I mean, there is no strong effect of the interaction. This region here, you have the phase transition, the superposition of the two regimes, where the magnetic field is 0 and the temperature is low, beta is large. There you have superposition of two phases, and there you have the most interesting thing, which is the critical point, where all sorts of interesting things happen. Okay? So if there is a need for that, I do it now. If there is no need, I go on. Since Alex doesn't want to be involved, I will ask Vladas, what should I do? No, okay. So again, let me summarize. We have this phase diagram. This is the order parameter. The behavior of, so let me say that again. This guy is a random variable, right? Because these guys are, so what you want to understand is the distribution of this random variable under the Gibbs measure, right? If you choose sigma, this is a function of sigma if you want. If you choose sigma under the Gibbs measure, what is the behavior of this random variable when n is large? That's the order parameter, and trust me, or come and ask me later, the behavior of this random variable rules the whole system. And that's why it's called the order parameter. And the interesting part is that in this whole region, this Mn here converges, I mean, has law of large number, Gaussian fluctuations, everything is simple. Here, the behavior of this variable is more interesting. And here it's even more interesting, the fluctuations are non-Gaussian. Okay, so that's the simplest model. And now that we have this, let's go to the models of spin glasses. So, mean field spin glasses. That's what I'm after here. Oh, by the way, I forgot to introduce this word. This is a mean field model. It's called mean field. Mean field because here, every spin interacts with every spin, right? I didn't say, so this, if you want, is a model on the complete graph with n vertices. You have n, you can imagine that this, if you want to see it geometrically, you can imagine that each of these spins is put on the vertex of a graph. And this graph is just the complete graph, which means everybody is neighbor to everybody. And then neighbors interact. Right? So here, since everybody is a neighbor to everybody, then everybody interacts with everybody. That's what mean field is about. Mean fields are modeled on complete graphs. And whereas you could think of the same model on the same model on a different graph, which would be, for instance, ZD, and that would be the Ising model. And now people would interact only with their neighbors on the graph, but now not everybody is neighbor to everybody. I won't go into the Ising model; it's a long story, but to just stress the similarities, is that the order parameter is the same object. It's the mean magnetization. And you have essentially the same type of phase diagram with a region here at low temperature and zero magnetization, zero external magnetic field, where you have phase coexistence, and here no phase coexistence. The Ising model is not at all trivial. This is trivial. All right? So the mean field model is supposed, as I said, to be very simple. So let's go now to the mean field spin glasses. So I start with the hard spin case, and then I'll go, so the first model would be this. So again, I take the same state space, configuration space. My configurations are a collection of n spins. It will be mean field again. And now I have to describe the energy. So the main feature is that we want to let go of this assumption, right? So we want J to, depend on the pair and maybe to be plus or to be minus, as I explained. You want the interaction, as I explained in my little speech before, to be sometimes ferromagnetic, you want the spin wanting to be aligned, and sometimes anti-ferromagnetic. So here's the simplest model that Sherrington and Kirkpatrick came up with. We said, let's take this. So let's put the interaction here, depending on I and j. Okay? Of course, I could put a minus, but since I said that this could be plus or minus, it makes no real difference. We could, of course, add an external magnetic field as before. We could even make this external magnetic field random and put it inside, but let's keep it like this. And what they wanted was this guy to be random. The Gij, so as I said, which are the coupling coefficients. So by simplifying this initial model I mentioned, remember we said that we wanted the coupling coefficient to be random and have random signs. So they are chosen, that's the important assumption here, to be IID. Okay, as I explained, from the physics of the model, being identically distributed is a reasonable assumption. Being independent is a very strong simplification. But that's what we do. Okay? IID variable, random variables. And the important thing, if you choose them to be IID but all positive, this would be called a random ferromagnet. It's ferromagnetic because they are positive, but random because the interactions are disordered. Right? So this is the disorder. This is what is called the disorder of the system. That's why it's called disordered media. So the randomness here comes from these guys. So if you want this function is itself random, I should put an omega if you want. If these guys depend on an omega. I would, of course, not use this omega. Here I have a random function. Right? But now we want these guys to have plus or minus, so typically we will assume that they are centered. Okay? And typically if we want things interesting, we want them, say, to be bounded, to have finite moments. I want to be precise here. Say at least 2, but for some proof we will need 3 or 4. So typically the model that they had in mind initially was I'm sorry? Not yet. Okay, so you have a keen eye. Something is missing here, but I'll come to that. Okay, the normalization is not yet there. As you've seen here, the normalization was n. All right, okay, if you want the normalization, let me put it there. It's this. And it's crucial that it's that. Okay, not n. All right, so okay, that's the only normalization under which something interesting happens. Okay, and I'll explain why. So that's the assumption that you need. So one, they are IID. Second, something about the fact that they have like that. And so typically what they wanted, they hope to solve J to be, say, +1, coupling to be +1 with probability half, and -1 with probability -half. -1 with probability half. Okay? So typically you choose your couplings to be plus or minus. This model was the first model. It was soon realized that it's simpler to study the case where and this is the case that we'll be studying here, to take the J's to be random Gaussian. Right? To be distributed as a standard Gaussian, mean zero variance 1. Okay. This model is what we will call the Sherrington-Kirkpatrick model. This is the +1 model. Okay, so that's the Sherrington-Kirkpatrick or SK model. All right, so let me come back to that. The couplings here are now IID and 0, 1. So why this normalization here? So, and why n over there? And square root of n here? A very simple way to understand the normalization is the following. You just look at what is the, so look at this, what is the field exerted by all the other spins on one spin, on one site, right? So this field is just simply sum of this Gij, sigma j. If you want, I can write this energy like this. Sum over I, sum over j of sigma j, sigma I, right? Let's forget the normalization for the moment. That's my energy. So I can look at this as something like sum of I is very rough. Some Hi sigma I, where Hi is this. And this Hi represents something like the magnetic field exerted by all the spins on the spin I. And if you want, it's clear at least that you should think that if you want this model to have some form of a limit, you want this magnetic field to converge to something, to be the right size, right? So in the Curie-Weiss model, this thing is simply 1 over n, let's forget the j, sum of sigma I, sum of sigma j, right? In fact, does not depend on I. And this is the right order of magnitude, because the law of large number takes care of this. The law of large number tells you that this is macroscopic. So the law of large number tells you that this is okay, right? You want to normalize by n, because this is of order n, typically. But now in the SK model, our Hi is 1 over square root of n, sum of Gij, sigma j. So let me put the normalization here. Right? And now it's the CLT that tells you this is the right normalization. Fix the sigma j. This thing now is a Gaussian variable of variance n. Right? So you have to divide by square root of n to have a limit. Right? And this limit will, of course, still keep some randomness in it. If you divide by n, you will just kill the whole interaction. If you divide by less, it will be huge. All right? So that's why you need the square root of n. All right, so that answers your question about the normalization. All right, let's forget this and go on. So we have now the Curie-Weiss model. The Sherrington-Kirkpatrick model. And we want to understand the two questions I asked. What is the limit of the free energy? How does the partition function behave? And how does the Gibbs measure behave? This looks like a trivial model. And as I said, it took something like 40 years to be really able to solve it. It's extraordinarily complicated. Whereas the Curie-Weiss is an exercise of, probability 1 to 1. This is probability 10, 10. So here is so this is one model. Here is a generalization of that, which will be very important for us. That's called the p-spin model. All right, so please, I start with this catalog of models, and then we'll study them. So let me define, so it's the same configuration space for the moment. And I introduce now this model. P is an integer. And it's given by that. Sum of j, I1, IP, sigma I1, sigma IP. And I sum of all the p tuples from 1 to n. And for the right normalization, I divide by p minus 1 over 2. All right, so what is this? And these guys, I'm sorry, the J, I1, IP are all IID and 0, 1. All right. So look at what this is. This is a p-spin interaction. Now it says the following. Instead of looking simply at one spin and another spin and at a pair interaction, now I could look at 3 spins. Right? And instead of looking at the product of their 2 values, I look at the product of the 3 values. Then this, I could also look at 4 spins. Right? So it's groups of larger size. That's the p-spin model. This normalization we will see is the right one. But of course, realize that Hn2 is the SK model. Right? If you take p equal 2, you're back into the model that was before there. And the normalization is correct. So this is a generalization of the SK model. That will be, so I'll talk about these models mainly, and p equal 2 is the case of the SK model. All right, so that's called a pure p-spin model. We'll see why it's called pure. And because right now I will get, so that was generalization 1, generalization 2. I call the mixed p-spin models. Or say general. So I do the following now, same sigma n, and now I consider the following. Hn of sigma will be the sum of beta p HNP of sigma. And I sum from p equal 1 to infinity. So now it means that my energy is a mixture. So I could have a term with p equal 2, p equal 3, p equal 4. So I look at interaction 2 by 2, 3 by 3, 4 by 4, and I just sum the whole thing. Right? So here, in order for this to be meaningful, because of course if I take a finite sum, that would be simple. If I want to be able to talk about infinite sum, I need some form of condition that the beta p decay fast enough. I don't want to dwell too much on that, so that this series is well defined. For instance, something like this is enough. Say the beta p decay exponentially fast. That would be enough. And if you don't want to deal with that, just assume that you have a finite number of beta p's. Right? So only finite. So this is the general class of model we're interested in. This, of course, contains the Sherrington-Kirkpatrick. It, of course, also contains the p-spin model by just taking one beta p. Right? So the parameters of the model here are the beta p's. In fact, I will encode this in the following function, which I will call nu of r, which is the sum over p of beta p square r to the p. So this function is very important. Of course, if I assume something like this will be defined, and for r, say, smaller than 1. So this function here will be the real parameter. So knowing the nu or knowing the betas are the same thing. This is the, if you want the Taylor expansion at 0 of nu. So if you, and so knowing this collection of things or that function is the same thing. If you take a finite number of beta p, this nu is a polynomial. All right? So what is nu for, so just in order for you to catch up with that, what is nu for the SK model? Nu of r is r squared. And for the pure p-spin, and nu of r is r to the p, because you have only one term. Right? The beta p's are all 0 except 1. All right? Look at the definition. Right? So nu is a monomial for the simple models, and for the SK model, it's just this r squared. All right, so that's the general model on the cube. And of course, again, the questions are, do we understand the partition function, the free energy? Do we understand the Gibbs measure? And the answer will be essentially yes for all these things. The understanding is not trivial, and the description even of the limits are seriously difficult, but we have results now. So that was my first class of model. So this class, remember, I will call that the general spin glass model on the cube. My spins are hard spins, and I take this general class. Here is another example, spherical models. So now, I take my configuration space to be the sphere of radius square root of n, as I described before. Right? And my measure alpha to be the uniform measure on it. Or Lebesgue on sigma n. Okay? Now, the energy that I will choose is exactly the same. The Hamiltonian, the general class, will be exactly the same. Sum of beta p, hn p of sigma. Because if you look at my definition of HNP, this is not only defined on the cube. This is defined on the whole of Rn. So in particular, this is defined on the sphere. Right? And remember, the cube was inside the sphere. So here, this model, in some sense, contains the points in the sphere, but I'm looking at the whole sphere. I add the symmetry, the orthogonal symmetry to it. Right? So I take exactly the same model, and now I have my Gibbs measure, and I have the same question as before, except that I'm working on a manifold now, the sphere, instead of a discrete object. Right? So my partition function now, instead of being a discrete sum, is now an integral. Right? So that's the spherical model, and we'll see that they are different. And then the third class, so this was the second class. Or maybe I won't go to the third class right now. Maybe let me just give you one model, which is supposed to be very simple. Or maybe not now, maybe not now. So let me, before we do anything else, explain why these models have structure. We came to them by starting from the Curie-Weiss type of thing and randomizing the interaction for reasons I explained came from the history of physics. Let me go there in a completely different way. I could introduce these models completely differently from a purely geometric point of view, at least in the sphere. Totally geometric. If you are pure mathematicians here, geometers or topologists, these models make sense on a purely topological or geometrical point of view, and with no motivations from physics, which is always good, that when you have a different view on it. So let me explain that. The real core computation that explains what I'm saying here is the following. You could look at either of these two models. I have this function, which is a random function. So I have a random function, Gaussian function, which is of course Gaussian function, which is my Hamiltonian or energy, Hn of sigma. I could add an omega if I wanted here to remember that it is random. The omega is of course hidden in the j's, right? That's the only place where you have randomness here. So you have this random function defined on space sigma n, which is either the cube or the sphere. And it's Gaussian, right? That is, the disorder is clearly, I chose all the j's to be Gaussian, so this is a Gaussian thing. The fact that it's a Gaussian field, if you want, in the probability world we tend to call these field, but it's in fact simply a function, helps tremendously. That's why this model is a priori much simpler than the +1 model. Why? Because in order, of course, to describe a Gaussian process, you only need to describe two things, which are its mean and its covariance structure. Right? Once you have the first two moments of anything Gaussian, you describe the law completely. So here, the first thing is, of course, that it's centered. If I take the expectation under the disorder of this thing, it's 0 for any sigma, right? Because I assume that the j's were centered. So when you take the mean of this, you get 0. And when you superpose a lot of them, you still get 0, right? Non-zero would mean that you add a magnetic field, which for the moment I've erased in all this computation. Right? If you add a magnetic field, then of course this would not be, the mean would not be 0. But let's, for the moment, assume that there is no magnetic field. So it's centered. So the only thing you want to compute is the covariance structure. And that's the key of this whole thing. So the computation is the same in the two models. So you want to compute the covariance of the value of this random function at the point sigma and at the point sigma prime. All right? So I'm claiming that this is something simple. With the normalization I have here, it's n times nu of 1 over n sigma inner product sigma prime. That's the core formula for the whole class, which is very simple but very important. Okay, that's the function nu. So the physicists call the inner product, they call 1 over n sigma dot sigma prime, which is just 1 over n sum over I of sigma prime I. They call this the overlap. Denoted by Rn typically, and it's called the overlap. It's very important to keep this notation. The overlap of the two configurations, sigma and sigma primes. Okay? So maybe that doesn't strike you as something fundamental, but it is. Because in fact, here is the geometric structure we have. So first, how do you compute this? Let's do it first. So the proof of that is very simple. Let's do it first for H and P, the pure case. So H equals H and P. Right? When you have, yeah. So how do you do that? Let's compute it. So you compute the covariance is just the expectation of Hn of sigma Hn P here, of sigma prime. That's what you want to compute. That's the covariance since the mean is 0. So you write what this is. This is sum. So you have n to the n p minus 1 over 2 multiplied by p minus 1 over 2. So you have 1 over n to the p minus 1. And then you have sum over I1 IP, sum over J1 JP of expectation of J I1 IP, J J1 JP, sigma I1 IP, sigma prime J1 JP. Right? I just expanded this whole thing and put the expectation inside. But then this is clear because what is this? Remember that the J's are IID, right? So they are independent and mean 0. So this thing is always 0, except if the two multi-indices are the same. Right? So this is just 1 over n to the p minus 1, sum over one set of index, I1 IP, and then J1 JP has to be the same, and this then becomes 1, it becomes the variance of J. And then you have sigma I1, sigma IP, sigma prime I1, sigma prime IP. Right? But this is just the sum of sigma I prime to the P. Right? If you expand this sum to the p, you get all these guys. Right? If you expand this to the p, you have sum of sigma. Okay, maybe I could, if you don't see that, let me do one more step. This is sum over I1 IP of sigma I1, sigma prime I1, sigma IP, sigma prime IP. Right? And this is, of course, I could write this as n divided by n to the p. So now this is n divided by n to the p, sum of sigma I, sigma prime I to the p. Right? I write it like this. You see this is just this p expansion of the pth power of a sum. And this is just exactly what I called Rn. This is just this is n, and this guy here is it's 1 over n sigma dot product sigma prime to the p. And this is, as you remember, nu of this. Because remember that in the pure case, nu of r was r to the p, which I described over there. Right? So the computation is made for the pure case. Right? But now, in a general case, you have nothing to do. Because the general case is just a superposition of these things. And the different j's are independent. So in order to compute a covariance like this, you just have to add them on p. And if you superpose them on p, you just get a superposition of this thing multiplied by beta p square, because it's a covariance. And then you just get this. So this proof is enough. Right? So we have proved that. And now let me explain why this, what the geometrical nature of this. The important thing is to realize that sigma dot sigma prime, when you are on the sphere of radius whatever, say n here, square root of n, which is the case for both models, this is in fact related to the distance. Right, so let's take first the case of the cube. If you are on the hard spin case, what is the natural distance in that? It's the Hamming distance. So the Hamming distance is, of course, simply the number of indices that differ. Right? It's the number of i's such that sigma I is different from sigma prime I. Right? That's the Hamming distance. It's, of course, also, this Hamming distance is really related to the Euclidean distance on the cube. So what is sigma prime, the overlap? The inner product. It's, of course, simply, when they are the same, this is 1. So it's the number of I such that sigma I equals sigma prime I multiplied by 1. And then when they are different, it's minus 1, minus the number of I such that sigma I is sigma prime I. Is different, I'm sorry. One is plus and the other is minus. Yeah, so this is n minus this number. So it's n minus 2 times the number of I such that sigma I is different from sigma prime I. Right? Because the sum of these two guys is n. Okay, so if you take the overlap now, which is the normalized inner product, is just 1 minus 2 over n, and this is the Hamming distance. Right? Or I could define the Hamming distance to be 1 over n times this, and then I would not have an n here. Right? So the overlap is in fact a function of the distance, the Hamming distance. And again, the Euclidean distance is a simple computation from the Hamming distance. So what we've seen here is that the covariance structure is a certain function, has the form n times a certain function, let me call it g, of the Hamming distance. Let me call it dh. which is the natural distance of the cube. That's the basic fact. Right? So we have this. The covariance is a function of the distance. Forget about the n. N is just a normalization. It's a function of the distance. Same thing on the cube, on the sphere. On the sphere, of course, and that would be the same here. If you have sigma n to be the sphere of radius square root of n, what is the, so you have the sphere here, you have two configurations, one here, one here. Their distance is, of course, simply the distance, the Euclidean distance of sigma and sigma prime is simply what? You project on the two, it's just this angle here multiplied by square root of n. Right? This length here is just the angle multiplied by square root of n, because the radius is square root of n times the angle between sigma and sigma prime. Right? And what is the inner product? Divided by n is just the cosine of that angle. Definition of the scalar product. So we see again that the overlap is a function of the distance. Right? So we have the fact again that the covariance at two different points is a certain function of the distance, maybe normalized by something. That's the same structure. So why is that important? Of course, again, so the function g here is easy to compute from the function nu. Of course, you cannot choose any g. Right? You have to choose a g such that this is a covariance. So you need a g such that this function is a positive definite function. Right? But we've found a class of things that work. But why is that important? So, and I will stop there. The only important thing here is the following. In general, if you have a Gaussian field or function, which is the same process, it in fact defines a natural metric on the space sigma. If I give you a Gaussian process, it defines a metric. What is the metric? The metric here is simply, let's say, the Gaussian metric, the metric associated with H. This natural metric, the Gaussian metric, is simply the expectation of H of sigma minus H of sigma prime square. This is the natural metric associated with the Gaussian process, which in fact rules all the properties of the Gaussian process. Its local property, the entropy, and so on. So in fact, a Gaussian process is really associated to a metric on a space. Here, of course, in our case, it's very simple, because when you expand this, of course, you get the expectation of this square. And by the way, in our models, you see that in any of these models, the variance is fixed. If you take sigma prime to be equal to sigma, this distance is, in all these models, this distance is 0, because sigma prime is sigma. So here you have a constant, g of 0. So the variance is constant here. Right? That's important to see that. The variance is a constant. With my notation is nu of 1, or with this notation is n g of 0. Okay? So it's a constant. So here you get n times this constant, nu of 1. For this square, this one gives the same thing, so you have 2. Right? And then you have minus 2, the covariance. And the covariance, we've said, is a function with an n of the distance. Right? So this is, forget the normalization, it's 2n times a constant minus g, or this is also g of 0 as I define it, I'm sorry. minus g of distance. So what I'm saying here is that the natural distance associated with a Gaussian process is in fact a function of the metric on the space. This Gaussian metric, which is intrinsic to the Gaussian process, is a certain function, well, let me call it phi, of the distance on the metric space I have here. That's the basic thing. So what does it say? It says that the two distances are topologically equivalent, right? Now, not equivalent, because they depend on this function phi, but they are at least topologically equivalent. Which means that the structure, the metric structure defined by the Gaussian process and the metric structure that you had a priori on your space are related. If you converge, if this goes to 0, then this will go to 0. So the two, otherwise, of course, and this is really, I mean, if you change your metric structure structurally on your space, then you should also look at a different class of processes, right? So this is really what is the basic fact in all these models. And we could start, and maybe we'll do next time, the other way around, saying, let me start defining what are the natural class of Gaussian function on a space which are related to the metric properties of the space. They should have this. This Gaussian distance should be a function of the metric on the space, which means that we should have the covariance being a function of the distance. What is the general class of functions like that we can get? Right? Here is a preview of the answer. On the sphere, it's essentially only the class we have here. So if you attack it from a geometrical point of view, you get exactly to the same models, right, that we built from the ground and the physics side. You have exactly it from the geometric, the same class from the geometric point of view. Okay? So everything we'll be doing, in fact, and I didn't introduce a third class of model, which is ultrametric. I'll explain next time what ultrametricity is. We will study three classes of model, in fact, which are just properties of things like this. This is the right way to frame it if you forget physics. It's, I look at Gaussian processes on metric spaces of large dimensions which have, which are related to the metric of the space by this. One thing to notice here, that this phi that we have here does not, apart from the normalization, which is just, as you've seen, this is just a normalization of the variance. You could divide all the energy by square root of n, and this n would disappear. The important thing is that this phi does not depend on n. It's essentially given by our function nu. Right? This nu does not depend on n. I didn't choose, I could have chosen the following. I could have chosen the beta p to also depend on n. Right? I didn't do that. In my model, the beta p's do not depend on n, and that's important. Because otherwise, this relation between the two metric structure will change with n. There is no reason that in the large n limit, you have any limit. The real parameter of the whole system here is nu, the collection of beta p's, and you don't want this parameter to change with n all the time. Right? That's important. You could generalize the model by having a nu depending on n, but then having a convergence result will probably need to have nu n to converge to something. Okay, so next time we'll start afresh with these models with no introduction, and we'll begin working on them. And next time is tomorrow, right?